Um, Yesterday I posted the recording of yesterday's class. I think I did, yes, in the group. Okay, so what do you guys know about total internal reflection? I know exams are on the head. You guys must have revised. You must be knowing the basic concept. So let's just continue from where you don't know. I mean, from where you are having problem. So tell me what do you know already? Yes, Zainab?
Total internal reflection is when like when an object, when the light reflects within the medium again, like not once, like multiple times maybe.
Okay. Okay. So, okay. Okay. Now, if for example, we have two media, two materials, let's say materials, okay? This is air and this is the boundary and then this is glass, for example. So if light, for example, this is the normal, okay? And this is the incident ray. This is the ray of incidence and it gets totally reflected, okay, with no refraction. Will we call this total internal reflection? Yes, Zainab?
No,
Why not?
because it's just reflecting off. Internal reflection would mean when it reflects like multiple times within the same medium. Like maybe
Now multiple times is not necessary. If you have only, if the light is getting reflected even once, totally, and internally, I'm giving you a hint, internally, that is, I mean, that's enough to make it to put it under the heading of total internal reflection. But why isn't this considered as total internal reflection? Why are we using the term internal? Yes, Aisha.
Because it doesn't go inside the glass.
Okay, so it has to go inside the glass. It has to be inside the glass.
Yes.
What if it is water? Then how would you
Then
say?
it would have to go inside the water.
Right. So that means, in science, we should use definitions and terms which are universally applicable. So what are we trying to say here? We are trying to say that the ray of incidence, total internal reflection, will take place only when the ray of incidence meaning the ray which is falling on the surface, is within the optically denser medium. For total internal reflection to take place, the ray of incidence has to be within the optically denser medium, which in this case is glass. And if it was water, then it would have been water. Okay, so therefore, this is not total internal reflection. This is just simple reflection. Okay, for total internal reflection, the diagram should be this way: air, water, or glass, or whatever, but it has to be optically denser than the air. Okay, and if this is the normal, the ray of incidence should be within this optically denser medium. Okay, and then now, again, we have done this in our previous chapter, that when a ray of incidence falls on the boundary between the two materials, there are two things that can happen to that ray. What are those two things? Yes, Yusra?
It is going to reflect or refract.
Exactly. It is either going to, not either, both. Both things happen. Both things happen at the same time. Okay. It depends upon the angle of incidence. And angle of incidence, we should keep revising our definitions. Angle of incidence is the angle between the incident ray and the normal. So this is the angle of incidence. Okay, so refraction, so some of the light, if the angle of incidence is is lower than the critical angle, I am introducing the term critical angle and we will discuss critical angle in a bit. But if the angle of incidence is smaller than critical angle, then there are two things that can happen to this incident ray. One is that it will get refracted. And so where will it refract? Towards the normal or away from the normal? Yes, Yusra?
Away from the normal.
Why? Because?
Because it is leaving from a denser to a rarer.
Right. And so the speed is increasing. It's going faster. The light is going faster. And so it would have continued this way if there was no hindrance, but now it will move away. And so it will refract away. Some of it will get reflected. Some of it will get reflected. Now, which one is more, whether you have more reflection or more refraction, depends upon the type of material you are talking about. It depends upon the type of material you're talking about. Like some of the materials does not allow the light to pass through at all. If, for example, you have opaque material, then of course there will be no light passing through it. All of it will get reflected. Okay, it depends upon the, if you're using a dull surface, then most of it will get absorbed. So in fact, there are three things happening here. Three things, not two, three things happening here. The light gets refracted, it gets reflected, and also some of it gets absorbed in the form of thermal energy. Don't forget that as well. So it depends. So which one is more will depend upon quite a lot of factors, one of which is the material, the color, the texture of this, these materials that are involved. Also depends upon the angle of incidence. Now what happens, remember, okay, another thing, refractive index. Let's recap real quick what refractive index is. What is refractive index? Does anybody remember? Yes, Nabil? What was refractive index? Okay, Yusra?
Miss, sign,
Yes, yes.
it is the speed of light in air or vacuum over speed of light in a medium.
Right. So, and what is the other way? What is the other way of defining it?
Sine of angle I over sine of angle R.
Very good. Okay, so speed of light in air or vacuum. So it's a ratio of the speed of light in air over the speed of light. I'm just light in that material, right? So this ratio will tell us the refractive index for that material. Do you think this is going to change if we change this angle? Does this ratio of the speed of light in air and the speed of light in that material, is it going to change?
No, miss. No,
No.
miss, it doesn't change.
Yeah, it doesn't change. Okay. Why is it that we consider air and vacuum same? Do you know this?
Yes. Yes, they are same.
Practically they are same. They're not exactly the same. They are not exactly the same, but practically we ignore this variation or difference, because practically speaking, we cannot have vacuum all the time created in the lab to observe the behavior of light. So we consider it almost equal to the behavior of light in air. So this is always going to stay constant. This is always going to stay constant. So the refractive index stays constant. And yes, another way of looking at refractive index is that it is a ratio of the sine of incidence over sine of refraction. But remember here, the incident ray is in the denser medium, okay? Whereas here, the angle of incidence in normal refraction, this angle of incidence is in air, is in the less dense medium. So to keep things simple, to avoid confusion, remember, air or vacuum is always going to be at the top of the fraction bar. You are always going to have the air or vacuum angle in the air, or the less dense medium is always going to be the numerator. Just remember it this way. So no matter where they draw the incident ray, remember the less dense medium is going to be the numerator, okay, to avoid confusion. So the sign of incidence. So the sign of incidence in this case is this, okay? And the angle of refraction is this. The angle of refraction is the angle between the refracted ray and the normal. So sine I over sine R. So if this is constant, if this is not changing, what happens when we increase the angle of incidence? How do you think this will change? if this has to stay constant. If this stays constant, we increase the angle of incidence. What happens to the angle of refraction, which is this?
Miss, may I?
Yes, Nabil?
It decreases.
Decreases. Okay, so if this is increasing, this is the refractive index should increase, right? If this increases alone, this should increase. And if this decreases, this will further increase it. So this will not stay constant then. Look at it this way. I'll give you an example. For example, sine I over sine 2 of some material is 1/2. Okay. So refractive index is 1/2. Okay. Now, if I increase the sine I by, let's suppose, 2, it increased to 2, but it had, and 1/2 is 0.5, right? This also should be 0.5. So if this has increased, this should become, for this to be 0.5, I should have 4, right? 2 1s are 2, 2 2s are 4. Only then it will stay 0.5. So can you see, when the numerator increase, the denominator also should increase. That means the angle of refraction should also increase, because remember, the denominator has the inverse effect. When it decreases, this increases. So this is already increasing. We want this to decrease it so that this stays constant. So the angle of refraction also increases. So as we increase the angle of incidence, the angle of refraction also increases. Okay. But remember, because the light is getting faster in air, and so it is moving away from the normal, the angle of refraction is increasing faster than the angle of incidence. Both are increasing. When incidence, the angle of incidence is increasing, and angle of refraction is also increasing, but angle of refraction increases faster. Okay, so now angle of incidence has not reached 90 yet. It has not reached 90 yet, but angle of refraction has already reached 90. Or you can say that the angle of refraction becomes 90 before the angle of incidence becomes 90. And I will show you a video. I got this excellent video. I loved it. So I'm gonna share it with you. And in that video, you can appreciate the fact how, when the angle of incidence is increasing, the angle of refraction is also increasing. But because the angle of refraction is increasing faster than the angle of incidence, it reaches 90 before. But let me explain it myself first, and then it will be easier for you to understand what that video is trying to show. So you understood this, right? So now if
Yes, I have a question.
Yes, please. Yes, go ahead. Yes.
In your previous diagram, you said that the 3 rays are moving. So 2 are reflection and 1 is refracted. So the third one you said that is absorbed. So how it is absorbed?
Beta, when light falls on anything, for example, sunlight, when sunlight falls on anything, doesn't it get hot? Right?
Yes, miss, it does.
Right. So why does it get hot? Because some of the light energy got converted into thermal energy. So I was talking about that. Yeah, I was talking about that. Remember, whenever there is an energy conversion, there is always heat produced. I mean, light does get converted into thermal energy. So that is why when you keep anything in sunlight, it gets hot, because light is getting converted into thermal energy. Okay, so as we increase the angle.
Ma'am, I have a question.
Yes. Yes, please, Muhammad.
Ma'am, can you go to the previous page?
Sorry, yeah, please don't ask for permission. You can leave whenever you want.
No, I said, can you go to the previous page?
Oh, okay, this one?
Yes.
Okay.
Here you said that air and vacuum would be in the numerator always, right?
Yes.
But you put water and glass in the numerator.
No, this was, see, No. Yeah, I was just trying to explain you why the angle of refraction increases as you increase the angle of incidence, right? I will, like I was not using this for this example. I was not using this for this example, and I will tell you in a bit when we will do this. Okay, critical angle and refractive index. Air and normal, and then glass and normal. Okay, so yeah,
Miss?
I was just trying to explain you why the angle of refraction increases as angle of incidence. Okay, I was just trying to explain you that relationship. Yes, Yusra?
Miss, refractive index always stays constant?
Yes, because the ratio of the speed of light in air over the speed of light in that material is constant. That is why. Okay, refractive index is going to stay constant. Okay, so now when the angle of incidence has reached a value, when the angle of incidence has reached a value where the angle of refraction is 90 degrees, that angle of incidence is called critical angle. This you already must be knowing, right? So critical angle definition is that it is that angle of incidence where angle of refraction is exactly 90 degrees to the normal. Okay, that is the simple definition of critical angle. Critical angle, I'm again repeating, critical angle is that angle of incidence where the angle of refraction is 90 degrees. Okay, now if you keep increasing this incidence beyond this critical angle, if you keep increasing the incidence, you stop having refraction. All the light now is getting reflected. You remember here, light was splitting into two. Some was getting refracted and some was getting reflected within the same material. Now, if the angle of incidence gets greater than the critical angle, then the light stops splitting into two. All the light, whatever is falling. Oh, let me make another one. So if I increase the angle of incidence, this angle of incidence, if I increase the angle of incidence, now refraction stops. All of it gets, sorry for the, so remember, this is reflection. So this will follow the law of reflection. And the law of reflection states that the angle of incidence is always equal to the angle of reflection. Okay, angle of incidence is always going to be equal to the angle of reflection. That is the law of reflection. Okay, so this is called total internal reflection. So understanding this, we can come up with a definition. You don't have to ratify the definition. If you understand, make sure you're using the right terms and you try to define it in your own words. So let me come up with my own definition. Let me define it. So now, right now, I'm defining it in my words. So total internal reflection is when the angle of incidence is greater than the critical angle. And so all the light is totally reflected inside, okay, with no light getting refracted. Okay, so if you mention a term with all its requirements, I don't think the examiner would cut any marks, and he will award you marks because the marks are according to the key terms and the concept, right? So this is called total internal reflection. So this happens when the angle of incidence is greater than the critical angle. And the critical angle, what is the critical angle? Muhammad? Yes,
It's the
Muhammad.
angle at which the refraction is 90 degree to the normal.
Yes, when angle of refraction is 90 degrees to the normal. Okay, so now I will show you that video, okay, which is showing exactly the same thing. So let me share my screen. And let me know if you cannot hear the video. Can you see my screen?
Yes, miss, we can.
Yes, miss.
Okay. And also let me know if you can hear me. Okay, so this is a semicircular block. Can you hear me?
Yes, we can hear you.
Okay, so this is a semicircular block. Okay, this guy has very beautifully marked all the angles, and now he is throwing light in the form of a single beam. And at this point, I will pause this, and at this point, he is falling. I mean, he's making the beam fall on this block perpendicularly. Okay, it is
I can't
falling.
hear the video.
No, you don't have to hear the video. You have to hear me. Can you hear me?
Yes.
Yes, miss.
Okay, yeah, this video is silent. This is a great video, perfect video. You know, he's not saying anything. He's just showing. So this is a beam which is falling perpendicularly, perpendicular meaning at 90-degree angle onto the block. And because it is falling perpendicularly, it is not bending. Can you see? All the beam is passing through and coming out of the other side. There is no refraction here. Can you see that? All the light is passing through it. 100% refraction. Sorry, what am I saying? Meaning no bending, sorry, no refraction at all. Okay, so it is just simply passing through. Okay, okay. And now observe what happens as
Yes.
and observe now what happens when he increases the angle of incidence. So can you see both the angle of refraction and the angle of incidence are increasing? But can you see that the angle of refraction is increasing faster? Angle of refraction is increasing faster. Why? Because the refracted ray is bending away from the normal. Okay. Both are increasing, but angle of refraction is increasing faster. And so here, another thing I want you to, let me take it back. I want you to appreciate another thing. Here at this point, also appreciate light is splitting into two. Can you see the reflected light ray?
Yes.
Yeah, so some light is getting, some light is getting reflected and most of it is getting refracted, but some is getting reflected as well. But also observe that when he reaches the critical angle, there is no refraction and all of it gets reflected. That's total internal reflection. So now this is critical angle. This is the critical angle. Why? Because now the refracted ray is exactly at 90 degrees. So can you see, you can see the cursor? Okay. So can you see this refracted ray is now exactly 90 degrees to the normal. Okay, so this is the critical angle. Also appreciate that the angle of reflection is exactly equal to the angle of incidence. Angle of reflection is exactly equal to the angle of incidence according to the law of reflection. Now he will further increase the angle of incidence beyond critical angle and see what happens now. So now this is simple law of reflection. As you increase the angle of incidence, the angle of reflection also increases. So as he's increasing the angle of incidence, angle of reflection is also increasing. Okay, that's it. Okay. So, okay, so now let me stop my sharing. Okay, another thing I want to show you before I stop sharing is this total internal reflection is made use of in different instruments, such as optical fibers, you know, the optical fibers, the Wi-Fi fibers that we use, and also in periscopes. Okay, we make use of the total internal reflection. The advantage of total internal reflection in these instruments is that all the light that falls gets reflected without any wastage. Okay, and so we use shiny surfaces to minimize absorption, to maximize reflection. So therefore they have given these optical fibers, so all the light that falls gets reflected multiple times, but whatever goes in comes out at the other end. So there is no wasting of energy or light does not get dim, or it does not decrease in intensity. We get 100%, no matter what the distance, no matter how long this fiber might be. Okay, also is used in endoscopes, okay, and periscopes. Um, so this, did you understand? Is there any question?
No, miss.
Okay, now we will, this is the same experiment that I just showed you. Same, you have a semicircular block, and this is a piece of paper, okay, and we have a source of light, and we make sure that the beam falls in the form of a single beam. Okay, my question is, and they have asked this question at the end of the chapter, why doesn't the light bend here? This is air, this is glass, right? So it should refract. Shouldn't it refract here? And even in the video, it wasn't bending. It was bending only here at this surface, not at this boundary. Yes, Aisha?
Because it's hitting the glass at 90 degrees, so it won't refract.
Very good. Yes. And how do we know that it's hitting at 90 degrees? Yes, Aisha? How do we know that it is hitting at 90 degrees? Remember, we did this before. How do we know if a line is perpendicular to a circle? So this is a circle, right? This is a part
we
of
make that line
tangent.
Yeah.
Yeah, no, you better know that term, okay? It's very important. What is a tangent?
It's when you make a line across, like on the outside the circle, and it's perpendicular to the radius.
Line passing through a center.
Line passing through the center is the radius. It's or a
The
diameter.
line should be perpendicular to
Line
the
made on the
radius.
circumference.
Sorry? Yes.
Line passing through the circumference of the circle.
No. Line touching the circumference at a point and is perpendicular to the radius. Like this is a tangent. So if this is the radius, it is perpendicular to it. Okay, and it is touching the circle at only one point. Okay, at only one point. Excuse me if my line is not exactly perpendicular, but what I mean to say is that a tangent is that line which touches the circle at one point and is perpendicular to the radius. That is a tangent. Okay, like for example, this. So you can see that this light is entering perpendicularly. So no matter where you make the beam of light fall, it is always going to be perpendicular to its tangent at that point. And therefore, the light does not bend at this boundary, but it bends at this boundary. Now, why does it bend at this boundary? Because here, as you can see, it has some angle of incidence. It is not perpendicular because the normal is here. This is the normal. ON is the normal. Okay, so you have this. So did you see how this is carried out in the video? This is the same setup. Okay, so why? Note the refracted ray emerging from LOM into the air and also the weak internally reflected ray in the glass. And we did observe the weak internally reflected ray in the glass in that video, right? Slowly rotate the paper so that the angle of incidence on LOM increases until total internal reflection just like this is the same which I just showed you in the video. Okay, so they keep increasing or decreasing the angle of incidence and they observe how the light is getting refracted on the other end. Okay, now let's move on to refractive index and critical angle. So we discussed what refractive index was. It was the ratio of the sign of angle between the ray and the normal in the air. So remember, air is always going to be in the numerator and the glass is always going to be in the denominator. And so, yes, Muhammad, you pointed out correctly that in that example, which I used to explain you, there, you know, yes, my incidence was in the glass, but it was in the numerator. But that was, you know, I was just explaining. But let's see how this turns out. So now, in case of total internal reflection, let's use this. This is included, right? This is in green shade, so this must be included. So if we know this, now in case of total internal reflection, the sign of angle between ray in glass and normal is the incident. This is the incident. Yes, but it stays in the denominator. It stays in the denominator. And so, okay, let me use some, let me use this. Yes, let me use this diagram. Okay, so n is equal to sine, I will just write air. Okay, angle in the air, whatever the incidence or what, that confuses me. Angle in the air and the angle in the glass. Okay, whatever that is. Okay, so now this is my diagram, I'm just using it. Angle in the air is 90. Angle in the air is 90, and so sine 90, and angle in the glass, whatever that is, I will, so that is critical angle, right? So I will use sine C. So now instead of I'm using, or instead of these symbols, I'm using C. C for critical angle. Okay, so that will give me the refractive index. Okay, now sine 90 is always 1. Sine 90 is always 1. Where have they? Here. Sine 90 is always 1. Okay, so I can write it as 1 over sine C. So that means this is another formula for refractive index. Refractive index is equal to the inverse of sine C, 1 over sine C. So if you know the critical angle, you can find out the refractive index. Or if you know the refractive index, you can find out the critical angle. Okay? Okay. Okay. Now they are just explaining, they're just talking about the total internal reflection being used in prisms, which are used in periscopes. Now what's happening here? Now what is the critical angle for glass? Critical angle of ordinary glass is about 42. Okay, remember this is a useful value. Okay, remember it. Usually the glass that they will talk about in the exam, its critical angle will be 42 degrees. So you can see here the angle of incidence is 45. Why is it 45? Because this is 45. Okay, and if this is 45, this is, and if this is 90, this is also 45. And if this is 45 and this is perpendicular, this is, you know, this is all geometry. So you know this is 45 and 40, this is angle of incidence is 45. So 45 is greater than 42. So the critical angle is 42. That means when the angle is greater than critical angle, there is total internal reflection with no refraction at all. Okay. And the angle of reflection is always going to be equal to the angle of incidence according to the law of reflection. So 45, 45, and you have line, this ray coming out the other surface of the prism. Now, why isn't it refracting here? Because again, it is perpendicular. It is hitting the boundary perpendicularly. Here also, it is hitting the boundary perpendicularly. So you will not see any refraction or any bending. Okay. Now, same is the case here, but their total internal reflection is taking place twice, here at this point and here. Why? Why? Because for normal is this, here at this surface, the normal is this. So the angle of incidence is this. okay, which I think is greater than 42. And so there is no refraction, but in fact, all the light is getting reflected. Here, where is the angle of incidence? Here, the normal is this. The angle of incidence is this, which I think is again greater than the critical angle. And so all the light is getting totally reflected. Okay, so this is how mirrors work in periscopes. This is how it is. Okay, now this here, they're
Miss,
talking, yes?
Miss, total internal reflection is from denser to rarer, or can also be from rarer to denser.
No. From denser to less dense.
So, Miss, for that diagram, the PQR diagram, for the A, you said that this is a total internal reflection, but it is going from rarer to denser.
No, beta, but the total internal reflection is taking place at this boundary, which is in which the light is entering from denser to less dense, not here. Here, there is no refraction or reflection, just simply passing through. Okay, total internal reflection is taking place at this boundary, PR. Okay,
Miss.
yes, where the light, so it will always happen when the incident ray or the falling ray is in the denser medium. Here in this case as well, the light is the internal reflection is taking place here at this boundary. Let me mark it as A and B, then it's easier. Okay, and then again here, when the light ray is hitting B and C. Okay, so from the denser medium to less dense medium. Okay, now this part, I don't know how important this is, but they're just talking about multiple images in mirror, and that is due to multiple refractions and reflections that take place within the glass, which is silvered at the back. The reason why the mirror is silvered at the back is to prevent the light getting out, I mean getting refracted the other side of the mirror, and so that all the light ray gets reflected so that we can see the image. So this is the main image, which is produced by the light getting reflected at the back of the glass. But then of course we have some reflection which takes place at the surface, which also produces an image. Okay, and then we have some internal reflection, there's some internal reflection going on, which also produces an image. So you don't have to go into the details. I don't remember coming across any past paper question talking about these multiple images, but this is all they're talking about. Okay, and then this picture is showing how these multiple images, I mean this is how you see multiple images. Okay, like, okay, so this gives you a blurry, this makes the image blurry. Okay, okay, so any question? Yes, Yusra, I can see your hand raised. Okay, let's move on to these end of chapter questions. Figure 30.7 shows rays of light in a semicircular glass block. Explain why the ray entering the glass at A is not bent as it enters. This we have already discussed. Anybody wants to revise? Maruj, you wanna tell us why the light is not bending at point A? Yes.
Because of
Yes.
the tangent.
Yes, because it is perpendicular, right? It is perpendicular to the boundary, right? At that point, it is perpendicular to the boundary. How do we know that it's perpendicular? Because it's perpendicular to the tangent drawn at that point. It is perpendicular to the tangent drawn at that point. Yes, Yusra, do you want to repeat what I just said?
Miss, I wanted to answer your question.
Yeah, okay, answer it. Yes, I want you to answer.
because it is perpendicular to the tangent, it is making a 90 degrees, so continue to travel straight.
Very good, perfect. Okay, part B. Explain why the ray AB is reflected at B and not refracted. This is easy. Ahmad. Why the ray AB is reflected and is not refracted. Easy. अभी सारा टॉपिक क्या पढ़ाया? यही तो पढ़ाया. Zainab, what happened? No hand raised. Come on. Nabil?
Please repeat the question, Miss.
Part B, explain why the ray AB, this AB, is reflected. All of it is reflected and none of it is refracted. This is what they're asking. That why is this AB?
Miss,
Yes?
may I?
Yes, okay.
Maybe it is because the angle of incidence is bigger than the critical angle.
Yes. Perfect. Yes, of course. This total internal reflection going on. यही तो पूछ रहे हैं ना. They will explain why the ray entering the glass at A is not bent. Explain why the ray AB is reflected at B and not refracted, because there is total internal reflection going on. What is total internal reflection? Like all the light is reflected, no refraction. Okay. Okay. Is everybody clear? Hiba? Is there any question? Please ask me right now. C. Ray CB does not stop at B. Copy the diagram and draw its approximate path after it leaves B. So who will tell me what will happen to ray CB? So there is total internal reflection going on at this angle AB, but if the angle is this small, yeah, he should start from Baba's room. So if the angle is this small, what do you expect? Yes, Aisha, very good.
The light would travel along the edge of the glass.
You mean 20 is the critical angle? Huh? Is that what you're thinking?
I just remember that when it's at that point, it travels along the edge.
Beta, for that, I mean, if it is 20 and if it is an ordinary glass prism, remember the ordinary glass prism has a critical angle of 42. 42, okay? So this is 20. So this is smaller than the critical angle. And so when the angle of incidence is smaller than critical angle, what happens? Yes, Maruj? Yes, Maruj?
It will pass through the lens.
It will pass through?
It will pass through the glass.
Pass through the glass. You mean reflected or refracted? Please use the term so that I know what.
Reflected.
Reflected?
It will reflect.
All of it?
Reflected.
All?
No, only some. And some would be reflected.
And some would be Yes, say it,
refracted.
Say it. Yes, some of it would be refracted, yes. So I am just drawing it here so that, okay. So this is CB. This is C, this is B, okay? So I will make it this way. This is not exactly 20 degrees, but I'm just, okay? So some of it will get reflected because the angle is still less than the critical angle. Some, it will split into two. There will be no total internal reflection, some reflection, and there will be refraction. So I will just make it this way. Something like this, okay? Or, and if you have to be exact in your diagram, you know how you should do? You should find out what the angle of refraction should be, and then with the help of a protractor, you should make that angle exactly. And how will you find out the angle of refraction? If you know the critical angle, the refractive index of the glass, then sine okay, so this, it would be sine I over sine R, okay, and then you can write sine 20 over sine R, and then this should be 42 degrees, and then you will solve this, and if you get, and this is how you will get the angle of refraction. And then after you have calculated it, you measure with the help of a protractor. But for that, this also should be exactly 20. Okay, this should be exactly 20. And so if the question asks you, if they mention, then no need to draw to scale, they just want to know if you know what's happening, what's going on, then this sort of a diagram would be enough. Yes, Yusra? Yes,
No,
Yusra?
Miss, I wanted to answer the question.
Oh, okay. So this is going to be my answer. I'm going to draw the path of CB this way. Okay. Now, question number 2. Copy figures 30.8 A and B and complete the paths of the rays through the glass prisms. Okay. So, okay, I tried to draw this. Again, this is not to scale exactly. So I copied this diagram. Okay, so what's happening? Let's see. The light is exactly perpendicular to this surface, so it won't bend. Okay, if it is exactly perpendicular, it won't bend, it will continue straight. But on this boundary, the angle of, there is some angle of incidence. I mean, it's not 90 degrees. So there will be refraction. But wait, the critical angle for glass is 42, right? So I should see if this angle is 42, or is it greater or less than 42. If it is greater than 42, then I will only show total internal reflection. And if it is less than 42, then I will show both refraction and total internal reflection. Okay, and if it is exactly 42, then also total internal, no, then I will not show anything. It will exactly be perpendicular to the normal. Okay, then I will not show anything. If the angle of incidence is exactly 42, then that means that the refracted ray is exactly at the boundary. Okay, so this will depend upon what the angle of incidence is here. Okay, so you will have to, measure with the help of protractor and everything. So part D. Now what's happening here? This, I think, is total internal reflection. Again, my diagram is not exact. Okay, here there will be no bending because the incident ray is falling perpendicularly on this. And then here, again, you will look at the angle of incidence. It looks, what does it look? It looks smaller than 42 to me. And if it is less than, no, is it greater than 42? So again, you have to look at the angle of incidence. Is it greater than 42? I think it is 45. If this angle is 45, according to them, this angle can also be 45. And if it is 45, that means it is greater than critical angle, and you will show total internal reflection. Okay. And again, at this boundary, again, you will show refraction, bending away from the normal. Bending away from the normal. So this is the normal at this boundary. So my diagram is not exact, but this is, but you should know, but you should show that you know what's happening here. So there's total internal reflection taking place at this boundary, and you have some refraction taking place at this boundary. The angle of incidence is going to be this. Oh, wait. Maybe there is total internal reflection this way. Huh? Like this. Like this. Yes, my diagram, I think my diagram is wrong. and you should draw this. This is the same, right? What do you guys say? Yes. Yes, you should draw this. Yeah, I got wrong here. Yeah. So, okay. The diagram should be this way. Okay, I'm just making, because I don't have time. We're running out of time. So if the ray is entering this, and then this, and then, so there is total internal reflection taking place at both. I just paid attention. When I teach, I realize a lot of things while teaching. That's why, teaching is so good. You learn yourself. So, there is total internal reflection taking place at this boundary as well as this boundary. So this is how periscopes work. Okay. So the normal are going to be this way. Okay. Normals are going to be this way. So the angle of incidence, these are angle of incidence. These are angle of incidence between the normal and the incident ray, between the normal and the incident ray. Again, this is the incident ray and this is the normal. So, and this is the incident and this is the normal. So these are the angle of incidences. Okay. And the angle of reflections are then these. These are the angle of reflections. Okay. They're going to be equal. So I think, yes, this is the correct diagram. That one was wrong. Okay. So this is total internal reflection going on in here. So how do you know if you have 45 degree angle, right angle, if the prism, you see that there is 90 degree here, 45, most probably total internal reflection, because the angle is going to be 45. The angles of incidence, according to geometry, is going to be 45, which is greater than the critical angle, which is 42. And therefore, you will show total internal reflection. Okay. Is there any question? Any confusion? Okay.
Miss?
Yes.
For part B, why didn't the light reflect and total internal reflection happened?
Yes, it happened.
No, but why did not reflect?
This is reflection. This is reflection.
Okay,
There is no refraction. No refraction here. Total internal reflection. Yusra, is there any confusion?
Yeah, miss, I don't get like why did not refract?
Because the angle of incidence was greater than the critical angle, because the critical angle is 42. And here the angle of incidence, all of them were 45. So yeah, I got a little wrong. I got wrong. Okay. And so I don't want you to get confused because of that. So these diagrams are not to scale. Okay, if you pick up a protractor and measure this, is not going to be 45. Okay, neither is it going to be 45 even in your book. I don't think this is 20 degrees. Let me check. This is, well, yes, it is 20 degrees. Okay, let me check this. Is this 45? Let me see. Oh, yes, it is 45. So, okay, your book has exact diagrams. No, this one is not 60. This one is not 60. This one is not 60. So some are to scale, but some are not. Okay. So, but you should know that when you have a right angle prism, the angle of incidence is going to be 45. Okay. According to geometry, you can, if you draw exact, diagrams with the help of protractor, you can find that out yourself. Okay. Is there any confusion? Okay, question number 3. Name 2 instruments that use prisms to reflect light. Well, we have endoscopes, periscopes, optical fibers. Okay, question number 4. Light travels up through a pond of water of critical angle 49 degrees. What happens at the surface if the angle of incidence is 30? So what happens? The critical angle is 49. This is water. Okay, this is air, this is normal. Okay, critical angle is 49. Okay, but the angle of incidence is 30. So now what will happen? Yes, Hiba, very good.
The ray will be refracted as the angle of incidence is smaller than the critical angle.
Okay, all of it will get refracted.
Some of it.
Yes, some of it will get refracted, but there will be some reflection as well. Okay, so I would draw it this way. Yeah, I would draw this way. This. So I will show that there is some reflection, and make sure if you're showing reflected ray, the angle of reflection should be equal to angle of incidence. This should also be 30, and this is angle of refraction. Because refraction and reflection both start with R, I would say that, use different symbols or maybe use the whole term. Refraction, and this is reflection. Okay, now what happens when the angle is 60 degrees? So 60 degree is greater than 49. Okay, yes, Hiba?
Total internal reflection.
Yes, total internal reflection. So that is easy to show. Don't show this, just solidify this line, and also okay, let me draw it. So just okay, this would show that this angle of incidence is 60 degrees. This should total internal reflection. This is also 60 degrees, and so that's that. Okay, total internal reflection. Okay, next question. Calculate the critical angle for water if n is equal to 4/3. Critical angle, okay. Critical, the formula is refractive index is equal to 1/sin c. Does anybody have a scientific calculator? So n is equal to 4/3, 1/sin c. So if I cross multiply, sorry, sin c multiplied by 4 is equal to 3. Sin c is equal to 3 divided by 4. Okay, and then c is equal to inverse sine 3/4. Do you guys have scientific calculator?
49.
48.6.
I can hear
48.
so many answers.
8.6.
Miss, the answer is 48.59.
48.6.
So if we round, it will be
8.6.
49.
Okay, we are chapter 30. Let me check from the back.
0.01.
Okay, let me check from the back. 48.6 is the answer. Are you guys getting 48.6 with this?
Yes, miss.
Yes, miss.
Okay, so this is easy, right? This is easy. So okay, we finished the chapter. Is there any confusion? I hope I didn't confuse you. Is there any question?